Good afternoon and welcome to today's Machine Design EHS Today and New Equipment Digest webinar titled Minimum Distances for Safety Control Measures, sponsored by Schmersal. I'm Nicole Stempak, Managing Editor of EHS Today and your moderator for the next 60 minutes. Before we begin, let me explain how you can participate in today's presentation. First, if you are having any technical difficulties during today's session, please submit them to the questions window and our technical experts will assist you. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with your webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send those in at any time. To do so, simply type your questions into the question window on the side of your screen and then hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design EHS Today and New Equipment Digest websites within the next 24 hours. You'll be notified by email when the archive is available. And I would now like to introduce our speaker for today's discussion. Devin Murray is the Technicum Services Manager for Schmersal's Engineering Services Group in North America. He has written many white papers related to safety standards and general machine guarding, conducted risk assessments and validations, and developed and reviewed the implementation of corporate safety standards. As a founding member of the company's Technicum team, Devin helped develop a curriculum of machine safety training courses and recently led Schmersal's successful efforts to be an IASET approved provider. Devin holds a Bachelor's of Science in Electrical Engineering and an MBA from Alfred University and is a TUV Certified Functional Safety Engineer for Machinery. Welcome, Devin, and without further ado, the floor is all yours.
Perfect. Thank you so much for that, Nicole. Thank you, everybody, for joining us on the webinar today, going over the minimum distance for safety of control measures. That was a great introduction, so I think we can go right ahead into the actual presentation. Again, as Nicole mentioned, please use the question field, and we will get to those questions at the end of the presentation. If for any reason I cannot get to your question, I'll definitely reach out to you individually in email to answer those questions for you. But looking at what we have in store this afternoon for the agenda, we're going to look at the need for machine safety distances, the minimum safety distances. We try to apply these control measures. We're going to look at some of the requirements and standards that are associated for us when we're trying to help determine where we need to place some of these guards and safety devices. We'll look at some methods to do the actual calculations and to properly implement these safety distances. And again, we will have some time for some Q&A. All right. So with the agenda, let's go ahead. We have 60 minutes here, and I want to give you a lot of important information. So the goal for this webinar to answer the question is, where do we place these hard guards and the safety devices that we're trying to implement on a machine or on a cell? And before we get to that question, let's first find out how do we get to that point. And whether it's for a new machine or system being designed today, or if it's an existing machine where you're looking at it and say, you know what, we're moving this machine, or there's a near miss or a history of accidents, or it's just time to do our machine safety assessments on our equipment, the approach will be the same. Okay. And that approach starts off like anything else with machine safety. It's doing that risk assessment. Okay. Now, we won't go over the entire process of what that risk assessment procedure is, but I definitely want to just highlight the hierarchy of control measures, because this is going to lead us to this discussion today for the minimum safe distances. All right. So when we look at a machine, we have to identify the hazards and risks, right? That's one of the first parts of a risk assessment. And when you identify the hazards and the risk associated with the equipment, you then have to remediate it. right? So it's one thing to point out what's wrong, but then it's also the next step to actually to correct the issue. So when we try to correct the issue with the machine guarding, it's, can we eliminate the hazard that we've identified? Okay, can we eliminate it? And this is why the risk assessment starts during the design phase, because if we can eliminate it during the design phase, perfect. Okay, if we can't eliminate the hazard, then we look into substituting the hazard. Okay, so for substitute for something that's a little less dangerous than this initial hazard that we've identified. And then we get into controls. So if we can't eliminate or we can't substitute, or if we can do a substitution but there's still room for improvement, we'll see if we can do some type of engineering controls. And that brings us to, part of this discussion here for today in this webinar. But before I continue on with engineering controls, let me just finish the hierarchy control measures. And if we can't successfully, remediate the hazards with the engineering controls, we then say, can we add some administrative controls, right? Some training, restrictive access, things of that nature. And then the last thing would be providing some type of PPE. Okay. But this idea of the control measure, again, if we're doing a design a new machine, we want to see, well, what type of control measures can we add to minimize exposure to this identified hazard? When we have an existing machine, same idea, right? Here's the hazard. What control measures can we implement to help protect against the hazard, help minimize exposure to this hazard? And that's what the entire life cycle of the equipment. Okay, so from the design all the way up to the decommissioning of that piece of equipment, and throughout several milestones. Again, if you're moving it, if you're changing a procedure or process, we have to do a risk assessment. But again, focusing on the engineering controls aspect of it. And when we look at the options for engineering controls within the industry, the first one that we always want to try to implement is the use of hard guards, right? The idea of separating guarding, and this is called separating guarding because it is physically separating you and the hazard. Okay, so there's a physical barrier there. And the reason that I say, what, can we get away with just using perimeter guarding? Is because at this point we're not tying into or tapping into any existing controls on an existing machine. And if it's a new machine, we're not adding any additional IO points because we don't have to have any additional interlocks at this point. Right now, we're just looking at some hard guards. And when we try to implement hard guards, these perimeter guarding, the fixed guarding, tonal guards, there are standards that we need to take into account. Yeah, that's with anything related to machine safety. There's always standards and regulations, requirements that we have to follow. And when you look at perimeter guarding, separating guarding, there is no difference. So there's something that we have to follow. And what I show here on the screen are two examples. And we have a international standard, ISO 13857, and we have a North American standard here, ANSI B11 9.19. And the reason that I want to focus on two standards specifically is because on this call, on this webinar, we may have a customer or a client or attendee, I should say, that is a global, has a global company, and you may want to focus on international standards so that all the different agencies globally are on the same page for machine safety. Of course, taking into account the local legislation, and then also on the webinar, we may have, a company that just focuses on the ANSI requirements. The good thing is though, as we start to look into some of these ANSI and ISO requirements and standards, there's not a huge difference. And the main reason for that is because they have the same goal in mind. It's trying to make sure that we are implementing these hard guards in the correct manner. All right, so we'll see what some of those differences are, but ISO 13857 is the safety of machinery, safety distances to prevent hazard zones being reached by upper and lower limbs, making sure that we cannot reach over a guard, okay, around the guard, under a guard, through a guard. ANSI 11.19 is the performance requirements for risk reduction measures, safeguarding, and other means of reducing risk. Now, NCB 1119, it's takes into a lot of different aspects for machine safety, and I'll explain that a little further on the next slide, where ISO 13857 is specifically looking at the distances and heights of the hard guard. NCB 1119 takes a little more, it incorporates a little more than just the heights and distances of the hard guard. Okay, but again, we'll focus some more on the standards as we go on with the webinar. The other side of a control measure, if it's not separating guarding, it's non-separating guarding. Okay, so here with non-separating guarding, there is no physical barrier between you and the hazard. All right, and examples would be like we show here: two-hand controls, light curtains, safety mats, safety scanners. There's nothing preventing you from reaching through a light curtain or walking through a light curtain, walking on a mat, walking past a scanner. And because there's nothing preventing you from essentially, reaching that point of operation, that hazardous point, there's certain things that we need to take into consideration, which is the distance. Where do we actually place these guards? And that is something that's overlooked a lot. We have a great intent to safeguard a machine, safeguard an area, and we have the great intent to utilize the technology in the industry. And then we say, okay, you know what? Let's use a light curtain, and we place light curtains at the perimeter of an access area. But did we do our due diligence as far as making sure the light curtain is placed at the right distance? Right? Did we do our due diligence to make sure the safety mat is of the right width so that we can easily step over it, or that once we actuate it, we're not going to be at that hazardous point while there's still a hazardous condition? So there are certain standards and requirements, just like for separating guarding, that we have to adhere to. For this, we have again an international standard and ANSI B 1119. So for the international standard, ISO 13855, that is the safety of machinery, positioning of safeguards with respect to the approach speeds of parts of the human body. So here we're looking at, again, walking past or through some type of safety device. And again, the same ANSI B1119 standard that we saw in the previous slide. Okay, and this is what I mean when I say that ANSI B1119 takes a lot of different machine safety aspects into account. This one standard looks at both separating guarding and non-separating guarding, where the ISO standards, we have two separate ones. Okay, again, we'll look into exactly what the differences are and how do we apply them. But the first thing is letting you know that there are standards and regulations in place that we need to follow. All right. When we look at separating guarding, again, there's a physical barrier between us and the hazard. There's certain things that we need to consider, and we list a few of them here. We have to make sure that we are not creating an additional hazard. And we've seen that before in the industry where, again, we have the good intent to safeguard a machine, safeguard a point of operation, but it's important to not create an additional hazard. And this is one of the reasons why when you do implement a control measure, you also have to do a post assessment to make sure that we aren't creating an additional hazard, right? So again, we want to make sure that we're not creating a crushing hazard, make sure that we're not creating a situation where someone can be trapped inside of an enclosed area. We want to also make sure that even though we're safeguarding the equipment, that we can still use the equipment. Okay, so if we still require access to certain parts of the machine, we have to take that into account with the hard guard, whether it's going to be a movable guard, a guard where maintenance can easily remove it, but operators cannot. All right, so we have to make sure that we can still access the machine as needed. We also want to make sure that we're not creating any type of ergonomic issues. Okay, so if we have to open a guard door, if the guard door is heavy, if it requires us to hold a part while we open and close the guard door, we have to take that into account. Make sure we have the correct materials for the guarding, depending on the environment. What type of application do we have? Is this a hazardous environment? Is this a high temperature environment? clean room environments. What type of materials are we using for the garden itself? And of course, the moment that we have a guard that can move, so some type of operator access door, that guard door has to be monitored. All right. And towards the end of the webinar, we'll also talk about what would be the safe minimum distance for a guard, even though there's an interlock on it. Okay. So that's something else that is often overlooked that we will discuss. Okay. Now, as far as these hard guards, and to answer the, start to answer the question on this webinar, as far as where do we place these guards? Okay. Um, both ISO 13855 and the ANSI 1119 will have a similar chart, if not the same chart, actually. And on this chart, we'll see that there is an area where it says, okay, what type of opening on this garden do you have, whether it's a slot, squared, or round opening? What's the size of this slot, squared, or round opening? And based off of those answers, it will tell you where you have to place this guard at a minimum. The idea behind this is that we want to make sure that we are not able to insert our finger, our hand, our arm through an opening and reach the hazards that we're trying to protect against. Okay. Again, we have the good intent here to safeguard a machine. We want to make sure that we're doing it correctly. We want to make sure that, yes, we have a mesh guard. Can we put our fingers through there and be exposed to a hazard? All right. So, that's what the standard says, and there are some notes here you see on the heading that we don't show. So this table is not complete. There are a couple of notes in there, but for the purpose of this webinar, let's look at what we have on the slide and try to apply it. Okay, so here's the example of a guard with some openings. If we try to use the table from the standards, the question is, what's the minimum distance we have to place this guard? Okay, so the first thing is, well, what type of opening do we have? Is this a slot, squared, or round opening? Right? Easy enough. That's a slot opening. Okay, and then the question is, well, what's the size of that opening? Well, it's 70 millimeters. 70 millimeters, according to this chart, is between 12 and 20. Easy enough, right? So the intersecting point on this table is 120 millimeters. This means that we have to place this guard at least 120 millimeters away from the identified hazard. Okay, that's also a key point. So we're not saying, or the standard's not saying, that we look at this machine and we have to be at least 120 millimeters around this entire machine. It's the hazard. Where is the hazard located? And that's also something that's um, either overlooked or not understood correctly. Where is the hazard? And this guarding now has to be 120 millimeters away from the identified hazard. Okay. Again, there's some notes in there and that we don't show. For example, right below the determined 120 millimeters, there's a 850 millimeters distance with the note in there, and essentially that note says, if the height of that slot opening is low enough that we can get closer to the hazard because your thumb will act as a stop. Okay, so again, we're just doing some screenshots, some high level views of the tables and charts to introduce them to you, let you know that they exist and how to use them. But of course, this is not a full training on it. So just keep in mind there are some notes within these standards that we have to consider as well. Okay. Um, when we look at how high and how high and how far the guard can be, we look at another table within these standards. And again, here the tables are going to be the same whether it's ISO or ANSI. Good thing about ANSI is that they have both millimeters and inches and feet for us, so we don't have to do any conversion. So this table that we're showing is strictly from the ISO standard because it's all millimeters. Okay, but before we even get into an example, if we think about what this table is trying to do, what the standard is trying to say, it's how high can we be without guard in relations to how close we are to the hazard and how high the hazard is. That's the goal behind the standards in this table. And if we just think about that for a second and we say, okay, we have a guard at X amount of feet, and we are this close from the hazard. The closer we get to the hazard, well, the higher the guard has to be so that we can't easily reach over it, right? The further we are from the hazard, the lower the guard can be, as long as we can't, easily step over it. And that's what the table and the standards is showing. And if we understand that and we look at again at an example, we could run through that, right? So here we have the height of the guard at 1800 millimeters. Okay, we have the height of the hazard at 1200 millimeters. Question is that minimum distance, right? How close can we be with this guard? The intersecting point on this table, 700 millimeters. So at minimum, we have to have a minimum safe distance at 700 millimeters. Okay, again, makes sense. All right. Um, if we look at it with another approach as far as the distances and heights, and we say, you know what, we have a height, a hazard of a height of 1200 millimeters. Okay, and we have a guarding, or we have that the height of the distance is 1100 millimeters. How high can our guard be? Okay, that may be another way we wanted to decide what type of control measure we want to implement. How high can the guard be? So based off the height of the hazard, based off the room that we have on the plant floor, we can say, all right, you know what? Based off these parameters, the height of our guard has to be at least 1400 millimeters. All right, and if we look at the picture up top that's been grayed out, we see that, all right, the further away you are from the hazard, the lower the guard can be. Okay. Again, if we think about what the standard is trying to say, that makes sense. That makes sense, right? Now, when we think about non-separating guarding, again, there's no physical barrier between us and the hazard. Again, there's certain things that we have to consider before we even start to think about applying such a device from the industry. We just have just three things here that you want to consider, and that's to make sure that this application does not allow for parts to be ejected or that there's flying debris. Why? There is no physical barrier, so there's nothing stopping a part being ejected from a machine, from a point of operation, and hitting someone. Right? There's nothing preventing flying debris from striking someone if it's from the operation. So if that's the case, then yeah, we need to look at hard guards, of course. If the application is free from things like this, we can continue and possibly look at some non-separating solutions. Okay. We want to make sure that the hazards cannot easily be accessed by reaching under, around, or through the guard, and that's the same thing for separating guarding. Right. We want to make sure that's not easily defeatable. Um, the key thing here, though, or one of the key things I'll say is that following the interruption of the safety device, we want to make sure, we have to make sure that the hazards that we're trying to guard against has ceased, right? Because again, there's nothing stopping us from walking past a laser scanner. So what we are expecting is once we walk past a laser scanner and I get to certain parts of the machine, that this machine is going to be in a safe state. The problem is that a lot of times these devices are installed without these considerations. And what we end up seeing is that there's this false sense of security. All right. And this can be well, not can be, this is a whole nother discussion, a whole nother hazard that we have to identify and address. Okay. And here's an example of that. Here's an animation that I'll show, but before I show the animation, let me explain what we are looking at. Right, so we have an individual here that's going to walk through a open area that's being monitored by a light curtain. We see that there's a green indication here that lets us know that there's power on the machine actuators, which means that there's going to be some type of motion. When I press play, we're going to see the gears inside of this hazard area move, which means that there's some type of motion. What we expect to happen is that when the person walks past this open area, they're going to interrupt the light curtain, right? Because they interrupt the light curtain, the safety outputs are going to drop out, the power to the machine actuators are going to drop out. And what we expect to happen is that by the time they get to the hazard area, the machine is stopped. We have a safe condition. Let's run through the animation. Okay, we have motion, machines running, and our individual here is going to walk past the light curtains, outputs drop out, but we still have some residual motion. Okay, this is a problem. This is a huge problem. When you went through a risk assessment, identified that there's a hazard, and identified that you want to add some control measures. So you look for the solutions within the industry. You say, you know what? Let's use light curtains. We use light curtains, but we didn't install them in the right distance. What exactly did we do as far as a control remediation or a risk reduction measure? So this is a problem. Right? The light curtains are placed at the incorrect distance. All right. The question is, how do we know what distance we need to place these light curtains to? Okay, to answer that question, we have to do a calculation, a safe minimum distance calculation. And this is from ISO 13855. Um, this standard is pages and pages of different formulas that are based off of S equals K times T plus C, and the formula changes based off the device that you're using. So if you're using a safety mat or a scanner or two-hand controls, the formula will be slightly different, but it all comes down to S equals K times T plus C, where S is the minimum distance that you are trying to determine. K is the parameter in millimeters per second of the approach speed of the human body. T is the overall stopping time of the machine, and I'll explain that a little further. And C is the intrusion distance, or how far past this safety device can we get before it actually registers that we are tripping it, right? So how far can we reach past the light curtain before we actually interrupt the beams? How far can we walk past through the scanner before we actually trip it? Right? This is this intrusion distance, and depending on the device and how we mount that device, again, this C factor will change. The overall formula may change slightly, but again, it comes back to S equals K times T plus C. Okay. ANSI B 11.19. The minimum distance that we're trying to determine is calculated by K times T plus D sub ds. All right. Again, K is the maximum speed for the body, human approach in the area. T is the total time until we reach a safe condition, and D sub ds again is that intrusion factor, or the older standards from B1119 called it the depth penetration factor. But DDS is again how far can we reach before the system detects that we are indeed interrupting the safety device. Okay. Again, there are certain elements with these formulas that we're not going to go into too much detail today. All right. Again, these standards themselves can be full blown training. Today we just want to highlight the key things we need to look at when we're trying to determine where do we place these safeguard solutions, whether it's a hard guard or a safety device. Okay. When we do a safe distance calculation, K times T plus C, okay, or D times T plus D sub ds, that T is the stopping time of the entire system. For that, we need to know what that stop time is, okay? When we look at devices that we're trying to implement for a machine or for a cell, there's certain things that we have to take into account because not every application would allow for a non-separating device. Okay, so we have to make sure that the equipment does not allow for full revolution before it stops. So if we try to implement a light curtain and we interrupt the light curtain, is that machine going to continue its cycle before it stops? If so, this is not going to be the right solution for it. Or there's going to be some other things we have to do to prevent or to stop that cycle from continuing. Okay. Um, we have to do a stop time analysis. Right. That's how we get that T factor. Is that stop time going to be consistent? If not, again, these non-separating devices may not be the solution for this application. That stop time has to be consistent, and we'll look at what that stop time calculation is. We think about the age of the equipment, so we can do the full-blown stop time analysis and the safe minimum distance calculation. But how old is this equipment? Right, and once we install a light curtain or install a device that's non-separating, 4 years, 5 years down the line, well, how much wear and tear was on this machine, right? The stop time is definitely going to change the more we use the devices on this machine, the motors, the belts, the drives. That's going to change. So, what's the age of this equipment? Can we actually apply a true, proper stop time analysis to determine the true stop time of the machine? The stop time. What is that actual procedure? Right? What are we looking at? What are we looking for? The stop time for the machine must be completed doing a scientific method. I always say. So the standard calls out doing using some type of stop and performance device, which must be calibrated if applicable. So some type of a stop time analysis, right? So again, some type of scientific procedure. And I say that because we are not going to use a stopwatch, right? We're not going to have someone use a stopwatch to try to measure the stop time of a machine. This is not feasible. We're not going to do that, right? So we have to do some type of scientific measurement, and it's not just one measurement. The standards call out at least 10 measurements. Okay, so we set up whatever we're using as far as the stop time analysis. We trip the safeguard solution. So again, the scanner, the mat, two-hand control, the e-stop. We trip it, and then we see how long it takes for the machine to reach a safe condition. Okay, a safe condition. We do that 10 times, and then we look at those measurements. And the standards say, both ANSI and ISO state that the highest measured value or the mean plus 3 standard deviations, whichever is greater, will be used as the machine stop time. Okay, so looking at the worst case scenario, what's the highest measured value at the of that 10 measurements, or what's the mean plus 3 standard deviations? Whatever's higher is going to be used for our T. As far as the procedures, the standards also call out what we need to have within the documentation. Right? So whoever's doing your stop time analysis has to follow these standards and make sure that they provide these parts of the documents for that test. That includes the machine identification, right? What type of machine we're looking at? What's the model? What's the serial number? That's for a new machine. That's for an existing machine. What type of engineering controls are we measuring against? What type of device is it? Right? Is it a light curtain? Is it a scanner? What type of measuring equipment are we using? Right? Are we using an encoder, a resolver, a high-speed camera? What type of device are we using? Has it been calibrated? What's that calibration date? Right? Date of the measurements. What are we doing for the calculations? Are we using the highest value? Or are we using the means plus 3 standard deviation? So a lot of these factors that, yeah, okay, that's a lot, but it's part of the requirements within the standards that's being called out. Okay, so yeah, it's one thing to take the measurements, it's another thing to actually document it correctly. Okay, but overall, again, coming back to the main part of this webinar, this conversation is we do our stop time analysis to determine what T is. We then take T and plop it into our equation to find out what that minimum distance has to be. On this slide, we have a combination of ANSI B1119 and ISO 13855 to show the differences between the equations. Again, this table is not in its entirety. All right, so there are certain parameters that we are not showing. For the sake of the conversation for this webinar, I'm just showing the parameters that correlate to each other one to one, essentially. Okay, so the distance to calculate for ANSI is D, for ISO it's S. Approach speeds, both are K. The total stopping time of the machine and its hazards is going to be T like Tango. All right. Here's where it starts to differ a little bit. The reaction time for the device is represented by T sub D of ANSI and T sub 1 for ISO. Okay, fine. That's the stop time for the actual safety component. We need to understand the stop time for the entire system. ANSI breaks it down a little more finer than ISO does. So ANSI says, okay, what's the response time of the interface device? What's the reaction time of the control system? The reaction time of the machine? We add all that up to get our T value. Where ISO 13855, yes, it looked at the same parameters, but the reaction time for the interface and the control measures and the machine is all lumped up into T sub 2. Okay. But again, we're looking at the same things, just grouped differently. The that intrusion factor, right? The depth penetration that's called out for the older ANSI standards is D sub DS, and for ISO it's C like Charlie. Those are the parameters. Again, not everything from ANSI. This table is from ANSI B1119, table H2. So you can definitely look at that standard in that table to see everything. That table also shows the older version of ANSI. So some of the terminologies changed. So it's a nice table to go through for a quick reference. Um, as far as that stopping time, again, that key element that we need to understand where we need to place these guards. All right, we need to understand the stopping time. Again, ISO 13855 on the left side of the screen, it's just two parameters, T sub 1, T sub 2. All right, what's the response time of the device that we're actuating? What's the response time of the machine? ANSI B1119, same idea, but we it breaks it down a little further. So it looks at the stop time of the device. We can get that from the manufacturer for a new machine, right? Or again, when we're doing our testing, we look at the response time of the device, the interface. So if it's is it going to a safety controller, safety PLC, is it just logic control? What's the response time of that interface element? The actuator controls. How long does it take for the power to dissipate? How long does it take for the actual motion of the machines to stop? Is there inertia on the equipment? So again, it's the same things that we're looking at between ISO 13855 and ANSI B1119. It's just ANSI breaks down a little further, which is usually rare, right? Usually the ISO standards that go a little further than our North American requirements. But here, great example of ANSI B1119 going a little further as far as trying to explain and dissect things compared to ISO. All right, so just like we did the example for the separating guarding, I want to look at an example for non-separating guarding. So for this example, we'll use a light curtain and we'll do our stop time analysis and say, okay, we have, zero point 0.3 seconds for the machine to come to a safe condition. The light curtain resolution that we want to use will be 30 millimeter resolution or 1.18 inches, which means that we can detect a hand. Okay, so we can detect a hand in here. Question is, where do we place these light curtains, right? What is the minimum distance? That's the question of the day. What is the minimum distance? So we use our formula, and the first one we're going to use is the ISO 13855. The formula again is S equals K times T plus C. The standard will give us K. So K is 2,000 millimeters per second. That's the speed of someone, all right? In this case, reaching through the light curtain. The standard will give us the formula for what that C factor is. Again, that C factor is going to change per device. So for the light curtain, the C factor is 8 times D minus 14, D being the resolution of the light curtain. Okay, so once we figure out exactly what these parameters are, it's just simple subtraction, multiplication, and addition, right? The key thing is what's that T value and what is C, right? What are they looking for? So once we understand that, it's just simple algebra, right? So again, the resolution is going to be D like delta. So we plop the 30 millimeter resolution in. And so it's 8 times 30 minus 14, which is a 128, which is the C factor. We plop that into our S equals K times T plus C equation states that the minimum distance is 728 millimeters. Okay, sounds good. Not just yet. Okay, so the standard says that if we do a calculation and that minimum distance exceeds 500 millimeters, which this case it does, we can go ahead and use the K value of 1600 millimeters. Right, so a little faster approach. And if we then plop 1600 millimeters into this equation, the C value stays the same, right? We're still looking at a 30 millimeter resolution. That distance then gets closer, right? It'll be 608 millimeters away from the hazard. Okay, not just from the machine, but from the hazard. Okay, if we then look at ANSI B1119, okay, D equals K times T plus D sub DS. What do we have? All right, so K, we're going to switch from millimeters per second to inches per second since we're using ANSI here. And we'll say the K value is 63 inches per second. That's given to us by ANSI. We do a stop time analysis again, and it's going to be 0.3 seconds. For ANSI B1119, for using a light curtain, D sub DS is going to be equivalent to D sub DT. Okay, just stick with me here, right? The formula for D sub dt is 3.4 times dE minus 2.75, where dE is going to be the resolution. Again, these two standards are looking at the same thing. It's just a different approach. We're going from millimeters to inches and whatnot, but it's the same goal. Where is the minimum distance for this light curtain? So we do the equation and we find out that D is equal to 21.98 inches. Okay, it's the same light curtain, same stop time, two different standards, and yes, the distance is not 1 to 1, so it's about what a 2 inch difference maybe, but the idea again is the same. All right, you just have to determine which one are you using for your company. Are you looking at the ANSI requirements, or we're looking at the ISO standards? Okay, we can't do both. Right? So we can't have one machine on one site, doing ISO, and then on the other side of the plant floor, we're using the ANSI requirements. So we have to be consistent. That's one thing. But which one you're using, it depends on your company and what you choose to use. Okay. All right. Now, once we do our stop time analysis, all right, as we saw on the previous slide, we can then put in that T value for the safe minimum distance, that K times T plus C, or that with the D sub DS. Okay, we can then put that in to actually know where we are placing this safety device. All right, when we do that, we see on this slide the grayed out area of where the original light curtains were. And we saw already that it was too close, because when the person went into the hazard area, they reached the point of operation. That machine has some residual motions. Yeah, we don't want that, right? So here we did the right calculations. We did the measurements in the right calculations, I should say. We then are able to place the light curtains at the right distance, so that when we walk through the light curtain, okay, by the time we get to that hazardous area, the machine is going to stop. Okay, and yes, this is an animation, and in most cases, when you walk past the light curtain, you visually are going to see the machine stop, right? So if you do the eyeball test, the light curtains are going to be perfectly fine, But when we do the actual stop time analysis, that's where we find out, is the light curtain placed at the right distance? Okay. Again, the intent is good. We want to apply some safeguard solutions, but we want to make sure that we're applying them correctly. All right. Um, one note here, or one last topic before we get into some Q&A. I'm looking at this side of the screen because I see a lot of questions coming in, which is perfect, and we'll have time to answer a lot of them. Um, if we look at a situation where we have a guard door without a lock-in device, okay, that means that at any point of the operation, we can open that guard door. Okay, that means that even though we're removing power from the actuators, like we did for the light curtain, there is a potential for residual hazards. ISO 13855 takes that into account. Okay, so it looks at that same formula, right? S equal K times T plus C. Okay, right now, again, we're looking at a system where we have hard guards in place. We have a movable guard that has a safety interlock on it. But if we open up that guard door, yes, we're going to send that stop signal, but are we going to be exposed to any residual hazards? That's the question. So we look at that same formula, S equals K times T plus C. The standard will give us K again. Okay. The T is the stopping time of the machine. So again, we do our stop time analysis. But here, what's different here is that we already established that we have perimeter guarding in place. And we have hard guards in place. This interlock device is installed on a hard guard. So for our C factor, we look at ISO 13857. Remember, that standard tells us how close we can be with our hard guards, right? If there's holes in there, right? If there's any type of opening, slot, squared, or round openings. Here, because we're using a fencing with slot, round, or square openings, but also the fact that we can open this guard door, not just reach our hand through, but physically open it and maybe reach our whole arm through, our walk through. We need to know, where do we place this perimeter guard, this access guard. Okay. And if you do your stop time analysis, or if you just, go through your risk assessment and identify that, yeah, this machine has high inertia, then we have to look at using means to bring that machine into a safe stop faster, or we look at using interlock devices that actually lock the guard door until we reach a safe condition. Okay, now this aspect on this slide, um, when we think about it, we do that already, right? When we safeguard a machine, when you're safeguarding a machine, you know that if the machine has high inertia, then you're gonna lock it, right? You're gonna lock until it reaches a safe state. But with most things, we look at standards, there's requirements behind the scenes that are in place that we don't even think about. We may do it on a day-to-day basis, but we don't even think about it. And here's one of those examples where, yeah, if we have a higher inertia machine, we interlock it, and this is called not out. Okay. Um, quick summary on answering that question, right? Where the safe minimum distance? Where do we place these? Whether it's a fixed guard, we want to make sure that we're at the right height, the right distance. If that guard has some openings in it, we want to make sure that we can't reach through it. ISO 13855, yeah, has a lot of different standard tables and charts. So does ISO 13857. So we only looked at two charts. And again, looking at the time, I'm glad we only did two charts. But the chart that we saw from 13857 is reaching through, right? Reaching your finger or your arm through, or reaching over. There's also tables in there to take into consideration reaching around, right? So if you can reach around the guard, the standard wants to make sure that you limit the motion of the hand, or limit the range of the hand or the arm or the forearm. So there's other things that we need to look at. Again, uh, just giving you a 10,000 foot view of these standards to help answer that question. What's the minimum distance for these solutions? Okay. You have to do a stop time analysis using some type of scientific method. We saw what's included inside the documentation, and with anything, whether it's perimeter guarding or a non-separating guarding, whatever control measure that we use, we want to make sure that we are not introducing another hazard. If we are, that triggers another risk assessment to do an additional risk reduction measures. Okay, that's a lot, right? Um, but like I said, I know there's some questions coming in. That's why I keep looking on this side of the screen. If you're looking at me on the camera, I will bring the call back and see if we can answer some of those questions. Again, if we can't get to all of them, we will definitely reach out to you individually. But yes, let's see if we can answer some of those questions in the time we have here.
All right. Thank you for that great presentation, Devin. As mentioned, several of you have submitted questions, so we'll jump right in. But as a reminder, you can submit a question by typing it into the question window on the side of your screen and hit the submit button. Okay, first step. How often are you supposed to conduct a stop time analysis?
How often are you supposed to conduct a stop time analysis? At most, annually. So annually, you should be conducting a stop time analysis, and then it also depends on the machine, right? Based off of your assessment, based off of the age of the machine, uh, you may have to do it a little more frequently to make sure that the light curtains, for example, are remain at the right distance. But the older the machine, the longer it starts to take to stop reach a safe condition. So we may need to bring it a little further away, I should say. So at most annually, sometimes a little more than that.
Okay, next question. Can you use manufacturer's information for the safety devices and machine components to calculate a stopping time?
Yes, you can. So for an existing machine, not so much because it's been in use, and the manufacturer data sheets. How old is that machine? Right? Is it 2 years, 5 years? We don't know that. For a new machine though, so you're designing a new machine and you want to go through your risk assessment process. We want to apply some scanners or light curtains. Yes, during that design phase, you can, because it's a new machine, so you can look at the data sheets for the drives and the motors and the safety device to calculate where that device should be, right? But to validate it, right? So once you do the designs and installation, to validate it, you still need to do your stop time analysis. But again, during the design phase, perfectly fine to use the manufacturer's data sheets.
Okay, next question. With the ANSI B1119 standard, is it mandatory to have an external review performed on the new piece of equipment versus conducting this in-house?
No, the main thing is that you are doing an assessment. Okay, as long as the person doing the review or doing the assessment understands what they're looking for, then it can be done in-house for sure. So it doesn't have to be a third party. If that was the requirement, that would be good for some people, for consultants, but it doesn't have to be. It can be somebody in-house that understands the requirements.
Okay. Next question. Do you use the smaller dimension when evaluating the slot opening?
Yes, you do. Right. So you look at the smaller. So if you look at the image that we used in the example, we have the height and then the width. The width was the smaller dimension. You use the small dimension for that table once you determine if it's a slot, round, or squared opening. So yes.
Okay, next question. Can you provide the guarding tables in inches instead of millimeters?
Yes. So the good thing about it is the ANSI standard, ANSI B1119, does have the table already broken up into millimeters and inches. The image that I showed was the ISO standard, but again, it's the same table with an ANSI that they use.
All right, great. Next question. Is there a standard chart for S and K, thinking slow reach versus running?
No. So when you look at ANSI B1119, it uses the 16 millimeters per second or 63 inches per second. With ISO, they start out using the 2000 millimeters per second, and like we saw in the example, if we do a calculation that's too high, then it states that we can use the 1600 millimeters. But again, look at ANSI is just straight there. Now, when you dive into the standards, it will say, like any other standard, based off of risk assessments and the application and the machine, you may have to use a faster speed. But again, that's based off the risk assessments. The bare minimum that they show you is going to be the 1600 millimeters or the 63 inches per second. But other than that, no, there's no defined table that says, okay, we need to use this or that. It's called out in the standard. Again, you may have to use something that's a little faster based on your application and risk assessment.
Okay, next question. How do ANSI and ISO standards relate to OSHA standards? And are there references that make these enforceable, including the stop time calculations?
Okay. So when you look at anything related to OSHA, right, there's we look at when the OSHA regulations were established, which was the 70s, right? And they do tell you to rely on these current relevant safety standards. And doing that, you are doing your due diligence. Okay, and when you talk about citations and OSHA regulations, they can always fall back to that general duty clause, right? You're not making a safe working environment. The ANSI table, right? We'll stick with ANSI since you mentioned OSHA. We look at the ANSI requirements. They have tables that have been updated since the OSHA tables, right? The OSHA tables take into account a whole different workforce over the years. So there's definitely been some updates to the tables. And if we use those ANSI requirements, again, we're showing that we're doing our due diligence, okay? With those ANSI standards, it does call out the fact that we have to use the stop time analysis, right? And it can be whatever way we use it, whether it's a high-speed camera or stop time analysis kit, but we have to go through those motions, right? And again, it's an ANSI standard, and OSHA can ding you, especially if we have the unfortunate situation where if someone does get injured when we have light curtains in place and there's an investigation conducted, and it turns out that we didn't do our full due diligence to make sure that we are providing a safe working place. So yes, and hopefully that it wasn't too long of an answer, and hopefully that does answer the question. That is a good question though, because I see that question a lot, right? A lot of these standards do call out a lot of requirements, and it's like, okay, well, do we have to follow these? And again, what we're looking at here right now is both ANSI and ISO, and ANSI is a North American regulation.
Okay, looks like we have time for just one more question rather. This person writes, I'm a machine designer. I need to design mounts for protection devices, such as light curtains prior to the machine being built. How can I design mounts and guarding systems if I have to measure stopping times of a hazard prior to placing the safety devices?
Perfect. Yeah. So in that situation, a new machine, you can rely on the data sheets from the manufacturers for that safety component, for the drives, things of that nature. You can pull that information and you can do that calculation. It's going to be a new machine. The device is going to be new, so the stop time is going to be dead on or very exact to what's called out in the mount and wiring instructions, and then you can use that as a basis on where you should mount those devices and guards. Yeah.
Okay. I'll do one last question because this one's pretty quick. Is there a certification required for a person to perform the calculations and stop timing per the standard?
Quick answer, no. You have to be certified, but you need to obviously know what you're doing, or you have to have an understanding of the standard and what the process is. But certified, you do not have to be certified.
All right. I'm afraid we have run out of time. For those questions we didn't have time to answer, Devin will be getting back to you via email. This concludes today's presentation. On behalf of Machine Design, EHS Today, and New Equipment Digest, I'd like to thank Devin for his presentation, Schmersal for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of your day, everyone. Take care.